This web lecture is to introduce you to the idea of neutral evolution. So this would be non-adaptive evolution, primarily through mutation and genetic drift. And neutral evolution is responsible for the vast majority of variation between individuals at the molecular level, and is also the most important factor in divergence between two species that are undergoing speciation once they've been genetically isolated. So this is a very important component of evolution as a whole. This week we're going to start considering the combined effects of different ones of these factors that can cause changes in allele frequencies. So in this case, we're going to be thinking about the combination of mutation and genetic drift. So we said in class that in terms of changing allele frequencies, mutation on its own is not going to have a very large effect. So one allele turns into a different allele. There's only one copy of that allele in the population at that point as a result of the mutation. That's going to change it from 0 to 1 in however many total number of alleles there are in that population. It's going to have just a very minute effect. But it's going to be a very important effect because once other forces start to work on that new allele, it could be natural selection or, as in this case, genetic drift, then we can start to see substantial changes in allele frequencies. So let's take a look at how this works. You saw this figure before when we were talking about mutations. So this is a particular case of point mutations, and point mutations can have a number of small or large effects depending on the kind of mutation you have. So you can have silent mutations, in which case you have exactly the same protein. You do have a new allele at the genetic level. This is not identical to the original codon, even though it's identical to the original protein, but at the genome level, you do have a new allele here. But it's not going to have any effect on evolution. It's going to be completely neutral with respect to natural selection. You can also have conservative missense mutations, which, remember, is the case where we do have a change in the amino acid that's coded for, but the amino acid is going to have very, very similar chemical properties to the original amino acid and will probably have a very minimal effect on the protein function. And so this will be a change, but a very small change. And so what we find, if we look at all of the mutations that occur, the majority of them are either neutral or very, very mildly deleterious. If they're beneficial, natural selection is going to increase their frequency. These silent or mildly deleterious mutations can be maintained in the population due to genetic drift. This process of substitution of neutral alleles by other alleles is illustrated by this figure from your book. So the columns represent the different alleles that are present, the different colors are different alleles, and then along the x-axis is generations, so time going along this way. So for a while, this yellow allele is the only one present in the population, and then at some point of time, you get a mutation to this green allele. So there are a number of things that can happen to this green allele at this point. If it's beneficial, it's going to be increased in frequency by natural selection. If it's strongly deleterious, it's going to be quickly removed from the population by natural selection. But if it's neutral or only mildly deleterious, there's a chance that genetic drift is going to, just by chance, increase the frequency of that allele. There's also a possibility that genetic drift by chance will just eliminate that allele from the population, even though it doesn't do any real harm. But if it does increase in frequency in the population over time, you can see genetic drift is carrying it to higher and higher frequencies, bouncing around a little bit. Genetic drift, remember, is completely random. But if you do happen to get to very high frequencies, eventually that green allele can completely replace the yellow allele completely by chance. In the meantime, you've had another mutation of green to purple, so green is not fixed in the population. There's another new allele in town, but it has effectively eliminated this yellow. We call this a substitution of green for yellow. And again, this is going to be completely random. It's not going to happen the same way in any two populations. So if you think about two populations diverging and becoming new species, there are going to be different alleles that are going to be replaced by new mutations in different ways in different populations, and this is the way you get most of the genetic variability that we see between species. You'll recall that one of the major learning objectives for this part of the course is to analyze circumstances under which evolutionary change will and will not happen, and make qualitative assessments of the relative rates of evolutionary change under different conditions. So if we think about neutral evolution, even though it's completely random, we can make some predictions about the rates of evolution under neutral evolution based on probabilities. And the way we do that is to think about the mutation rates and the probability that each new mutation is going to become fixed in the population. So the punchline of all of this is basically that we can say that the rate of neutral evolution is going to be roughly equal to the rate of neutral mutations. So these are mutations that are not going to be impacted by the effects of natural selection. So how do we get there? So let's start with a population with n individuals in it. So at each locus, in a population with n individuals, the total number of alleles at that locus is going to be equal to 2n, 2 alleles at each locus for a diploid organism. And let's call the rate of neutral mutations the Greek letter nu. So nu is going to represent the rate of neutral mutations at that particular locus. Remember, different loci can have different mutation rates. And so the total number of new alleles created by mutation in each generation, so this is across the whole population at that particular locus, is going to be equal to the number of alleles in the population, 2n, times the mutation rate at that locus, nu. So 2n times nu. If genetic drift is the only evolutionary mechanism, so this mutation is not going to be affected at all by selection, the probability of an allele drifting to fixation is going to be equal to the frequency of the allele, and we'll actually work through the argument that shows that that's true in class this week. So at the time that the mutation happens, there's only one copy of that new allele in the whole population, and so its allele frequency is 1 divided by 2n. There's one copy of this allele in the whole population of 2n alleles. So in each generation, the number of new mutations that are going to drift to fixation is going to be the number of new alleles created in the population each generation times the probability that each one of those new alleles will become fixed in the population, which is equal to its frequency in the population at the time of the mutation. So 1 divided by 2n, which when we cancel out the 2n, we're left with just nu, the neutral mutation rate. So we've just shown mathematically that the rate of evolution by genetic drift is going to be equal to the neutral mutation rate, the silent substitution rate. And again, this is going to be responsible for the vast majority of the molecular level variability that we see in populations.